Morning, students. After 1 week, so we have to take the DPTS class. Ending session of the second unit, that is performance of transmission line. We already discussed about the once I recall just 5 minutes total second unit performance of transmission line syllabus. First, we define the classification short, medium, long. Then we define regulation and efficiency. So now regulation efficiency will be applicable, regulation efficiency calculation and also sending end current calculation, sending end power, right? All the calculations for short transmission line, for medium transmission line. In medium transmission line, end condenser method, Nominal-T method, Nominal-π method. Then go for the long transmission line, calculation of voltage regulation and efficiency for long transmission line. That is a rigorous method. After then, we have to discuss about some problems calculating the regulation, efficiency, sending end current for end condenser method, Nominal-π method, Nominal-T method, right? So after then, we will discuss about the generalized constants of transmission lines. What are the generalized constants of transmission lines? ABCD constants of transmission line. That is nothing but two-port network. How our power system transmission concept must be applicable to two-port network. So VS is equal to AVR plus BIR, IS is equal to CVR plus DIR. That means we know the receiving end voltage, we know the receiving end current. By using the two values, you have to determine the sending end voltage and sending end current with the help of ABCD constants. Further, to calculate, why? Because we know the receiving end. That's why for phasor diagram also take the reference for receiving end voltage, and current IR is lagging the VR by some angle. After then IRR drop, IRXL drop, that may be adding to the VR. That means VR plus IRR plus IRXL is nothing but sending end voltage. From that, sending end current, sending end power factor, but efficiency VRIR cos pi r by VRIR cos pi r plus losses 3I square copper loss, right? Like that, we have to discuss it and solve the problems also. Now ABCD constants for short transmission line, ABCD constants for medium transmission, that is Nominal-T, Nominal-π, right? ABCD constants for long transmission. So the theoretical concept will be explained already. So what are the ABCD constants for short transmission line? Short transmission line lo etuvanti capacitive network undadu kabatti adi mottham complete ga series circuit. Because of short distance, because of less than 80 kilometers, the transmission line classified as short transmission line. So in this short transmission line, the capacitive effect is negligible. That's why there is no shunt branch. Only transmission line parameter, that means resistance and inductance, RL plus JXL. That's why sending end current is equal to sending end receiving current. IS is equal to IR, right? Gurtundamma. సో అప్పుడు ఏమైంది, దాన్ని మనం అప్లై కేవీఎల్ చేస్తే విఎస్ ఈజ్ ఈక్వల్ టు విఆర్ ప్లస్ ఐఆర్ జెడ్. ఓకేనా? ఈ రెండు ఈక్వేషన్లు మనం స్టాండర్డ్ ఈక్వేషన్స్తో కంపేర్ చేసుకుంటే ఏ ఈజ్ ఈక్వల్ టు 1, డి ఈజ్ ఈక్వల్ టు 1, బి ఈజ్ ఈక్వల్ టు సి ఈజ్ ఈక్వల్ టు 0. For short transmission line, the ABCD parameters are A equal to D equal to 1, B equal to Z, C equal to 0. B ఎప్పుడు కూడా ఏడి యూనిట్లెస్, బి అనేది ఇంపిడెన్స్, ఐ మీన్ ఓమ్, సి అనే దానికి మో ఆర్ సీమెన్స్. సో ఇక్కడ ఈ షార్ట్ ట్రాన్స్మిషన్ లైన్లో సి ఎందుకు 0 అయింది ఈజీగా చెప్పచ్చు. దెర్ ఇస్ నో కెపాసిటీ ఎఫెక్ట్, దెర్ ఇస్ నో షంట్ అడ్మిటెన్స్ బ్రాంచ్. There is no shunt admittance branch is nothing but there is no the C is equal to 0 easily. So very important for competition exam for 1 mark. What are the ABCD constants for short transmission line? A equal to D equal to 1, B equal to 0, sorry B equal to Z, C equal to 0, right? Then go for the medium transmission line, Nominal-T method. Here Nominal-T method is nothing but here the distance is medium transmission line is nothing but distance is between 80 kilometers to 150 kilometers, right, or 160 kilometers. So capacitor effect is considered. That means a capacitor is connected in between the line that may divide the transmission line into two halves. అంటే Z కాస్త Z/2 అవుతుంది. దట్ ఈస్ నథింగ్ బట్ R/2 XL/2. అదేవిధంగా R/2 XL/2, రైట్? R/2 XL/2, R/2 XL/2. మిడిల్లో కెపాసిటీ ఉంటుంది. దట్ ఈస్ నథింగ్ బట్ సో అడ్మిటెన్స్ C ఈజ్ ఈక్వల్ టు, ఇక్కడ మనకు 2 లూప్స్ వస్తాయి, ఒక లూపు ఇంకొక లూపు. దెన్ అప్లై ది KCL. IC ఈజ్ ఈక్వల్ టు IS మైనస్ IR ఒక ఈక్వేషను, VS ఈజ్ ఈక్వల్ టు V1 ప్లస్ IS ఇంటూ Z/2 ఒక ఈక్వేషను, V1 ఈజ్ ఈక్వల్ టు, V1 ఈజ్ నథింగ్ బట్ వోల్టేజ్ అక్రాస్ కెపాసిటర్, V1 ఈజ్ ఈక్వల్ టు VR ప్లస్ IR Z/2. By using these three equations, we have to combine, recollect and rearrange all these things, substitute one and equations. We are getting ABCD parameters of Nominal-T method. What are the ABCD parameters for Nominal-T method? A is equal to D is equal to 1 plus YZ/2. A is equal to D is equal to 1 plus YZ/2. B is equal to Z into 1 plus YZ/4. C is equal to Y. A equal to D equal to 1 plus YZ/2. These A, D values are not changed even though it is a Nominal-T or Nominal-π. A equal to D equal to 1 plus YZ/2. Just remember. Then B is equal to Z into 1 plus YZ/4. C is equal to Y for Nominal-T. Right? And we have to apply the symmetry and reciprocity conditions. Both are applicable. Then go for the Nominal-π. Nominal-T capacitor is placed in the middle of the transmission line that may divide the transmission line into two parts. అంటే అక్కడ ట్రాన్స్మిషన్ లైన్ 2 పార్ట్స్గా డివైడ్ అయింది. ట్రాన్స్మిషన్ ఇంపిడెన్స్ Z కాస్త Z/2గా మారింది Nominal-Tలో. బట్ ఇక్కడ Nominal-πలో అలా కాదు, కెపాసిటరే డివైడ్ అవుద్ది, ట్రాన్స్మిషన్ లైన్కి ఏం టచ్ లేదు. ఏ కెపాసిటీ ఇస్ డివైడెడ్ ఇంటూ 2 halves, C/2 C/2 లేదా Y/2 Y/2. Y is nothing but admittance across the capacitor, Y/2 Y/2. Now one half of the capacitor is connected at the sending end, across the sending end. Remaining half is connected across the receiving end. There is no change in the transmission line impedance, that is Z. Now what are the ABCD constants for Nominal-π? A equal to D equal to 1 plus YZ/2, there is no change, but B is equal to Z only. C is equal to Y into 1 plus YZ/4, right? Just small change. A equal to D equal to 1 plus YZ/2 for Nominal-T, Nominal-π. B equal to Z into 1 plus YZ/4. ఇక్కడ C equal to Y into 1 plus YZ/4. ఆ 1 plus YZ/4 అంటే జస్ట్ రిప్లేస్ అవుతుంది. ఆ విధంగా ఈజీ గుర్తుపెట్టుకుంటే గేట్ ఎగ్జామ్లో 2 మార్క్స్కి లేదా 1 మార్క్ ఇస్తుంది. ఐడెంటిఫై ది ABCD కాన్స్టెంట్స్ ఫర్ Nominal-T. అక్కడ మనం డెరైవ్ చేసుకుంటా టైం వేస్ట్ చేసుకోలేము కాబట్టి జస్ట్ రిమెంబర్, జస్ట్ మనం గుర్తుపెట్టుకోవడం, మన ఐక్యూని పెంచుకొని A equal to D equal to 1 plus YZ/2, B is equal to Z into 1 plus YZ/4, C is equal to Y. ఇప్పుడు ఈ 1 plus YZ/4 అనేది అక్కడికి వెళ్ళిపోద్ది Nominal-πలో అంటే జస్ట్ రైట్. సో ఈ విధంగా మనం అదేవిధంగా లాంగ్ బోర్డ్ చూసాం, కొన్ని ప్రాబ్లమ్స్ కూడా చేసాం రైట్. ఇప్పుడు మనం ఇంకొన్ని ప్రాబ్లమ్స్ చూసుకున్నాం. ఆ తర్వాత ఇంకా టాపిక్స్ ఉన్నాయి. ఫెరాంటి ఎఫెక్ట్, దాని తర్వాత సర్జ్ ఇంపిడెన్స్, దాని తర్వాత సర్జ్ ఇంపిడెన్స్ లోడింగ్, ఛార్జింగ్ కరెంట్. నేను మీ సీనియర్స్కి ఈ మూడింటి మీదనే వచ్చింది. ఎక్స్ప్లెయిన్ ది సర్జ్ ఇంపిడెన్స్ లోడింగ్ అండ్ ఇది నేను క్వశ్చన్ పేపర్ ఈరోజు పెడతాను, చూడండి మీరు రైట్. గో ఫర్ ది టుడే క్లాస్, దట్ ఈస్ ద ప్రాబ్లమ్స్. సో జస్ట్ గో ఫర్ ది ప్రాబ్లమ్స్. ఆల్రెడీ ఆ ప్రాబ్లమ్ మనం డిస్కస్ చేసాం. ప్రాబ్లం పోయే ముందు మనం మన టాపిక్ ఫెరాంటి ఎఫెక్ట్ గురించి చెప్పుకుందాం. బిఫోర్ దట్ వన్, what are the difference between Nominal-T and Nominal-π methods? They asking 2 marks, sometimes they asking 5 marks also. Suppose they asking 2 marks, just define the Nominal-T, Nominal-π. Suppose they asking 5 marks, just derive the values also, right? So already discussed. Now what is the nominal-T is nothing but the whole capacitance is placed at the middle of the transmission line. So the whole capacitance is placed at the middle of the transmission line that may divide the network into two halves. That is nothing but nominal-T. Whereas nominal-π capacity is divided. Half of the capacity is connected to the sending end, half of the capacity is connected to the receiving end. Right? That is only difference for 2 marks. That's enough. Otherwise, you have to draw the nominal-T and nominal-π networks also. They will don't reduce the marks. Define the nominal-T and nominal-π. Again, here we have to draw the nominal-T and nominal-π circuits, networks. Right? So now go for the important topic in first unit. So we will discuss about the two effects: skin effect, proximity effect. Right? Now, second unit, Ferranti effect. 3 effects: skin effect, proximity effect, Ferranti effect. They are asking 2 marks, they are asking 5 marks, whatever it may be. More important, and Ferranti effect is also more important for competition exams. Right? What is the Ferranti effect? Generally, the voltage at the sending end, voltage at the receiving end is greater than the sending end voltage. There is nothing but VR is greater than VS. VR is greater than VS. So at that time, the effect is called as Ferranti effect. Such type of effect is mainly occurs because the light load condition or open circuit condition. So at light load conditions or no load conditions, the receiving end voltage is greater than the sending end voltage. This effect is called Ferranti effect. VR is greater than VS, right? Mainly, why the Ferranti effect occurs in the transmission line? Mainly because of charging current in the transmission line. Whenever we are applying alternating voltage to the transmission line, the current that follows into the capacitor, the current flowing through the capacitor is called charging current. This charging current is also known as capacitive current also. Because of this charging current, so in the transmission line, when the receiving end voltage is greater than the sending end voltage. What is the Ferranti effect? What is the definition? At light load conditions or at no load conditions, the receiving end voltage is greater than the sending end voltage. So this effect is called Ferranti effect. Why? What is the basic reason for occurring of Ferranti effect in the transmission line is nothing but because of charging current or capacitive current. Whenever we are applying a transmission AC current, AC alternating voltage to the transmission line, that may give the current, that current is flowing through the capacitive. So that current is called capacitive current or charging current. Because of that charging current, the receiving end voltage is greater than sending end voltage. How it is occurring, we have to discuss it now. A capacitive or inductance are the main parameters of the transmission already discussed in the first unit. And we also derived the formulas for single phase, 3-phase symmetric, 3-phase asymmetric effect of it also, right? The greater line is greater than 240 kilometers and above, the effects are more pronounced. That means capacitance is not concentrated at some definite points and it is distributed uniformly through the whole length of the line. When the alternating voltage is applied to the sending end, the current drawn by the capacitor of the line is more than the current associated by the load. Load current kante capacitive current ఎక్కువగా ఉంటుంది. The voltage at the receiving end is quite larger than the voltage at the sending end. A charging current వల్లే basic గా receiving end voltage అనేది ఎక్కువగా ఉంటుంది sending end current కంటే. So at no load condition or light load conditions, the receiving end voltage is greater than the sending end voltage. That is nothing but Ferranti effect. ఎందుకు వస్తుందంటే ఛార్జింగ్ కరెంట్ వల్ల. So now I have to suppose they asking 2 marks. Just definition is enough. Don't read all these things. They are asking 2 marks. So at no load condition or light load conditions, the receiving end voltage of the transmission line is greater than the sending end voltage of the transmission line. It is known as Ferranti effect. VR is greater than VS. Enough. Suppose they are asking 5 marks, just we have to give a brief explanation also, right? A long transmission lines draw a sufficient charging current, right? That's why VR is greater than VS, right? Such a line is open circuit or light load conditions. ఎప్పుడు అక్కడ అవుతుందయా Ferranti effect అంటే లైట్ లోడ్ కండిషన్స్ లేదా నో లోడ్ కండిషన్ అక్కడ అవుతుంది, రైట్? So the receiving end voltage greater than sending end voltage, this effect is known as Ferranti effect, and it is because of charging current only, right? Therefore, both capacitance and inductance is responsible to produce this phenomena. Capacitance, that is nothing but charging current, is negligible in short transmission line. Why? Because there is no capacitance in short transmission, but medium and long we have to consider. Therefore, this phenomena occurs only medium and long lines, right? Charging current because of capacitance. Capacitance is negligible in short transmission. That's why there is no Ferranti effect in short transmission line. Ferranti effect is applicable to only medium and long transmission lines. Look at the figure. This is the Nominal-π method, and this is the phasor diagram for Ferranti effect. Here OM, OP, MN, PN, OC. So main OM receiving end voltage VR, OC current drawn by the capacitor IC, MN resistance drop, NP inductive reactance drop, OP sending end voltage, right? So we have to negligible, resistance is small compared to the reactance. Resistance is small compared to the reactance, right? So that's why resistance can be neglected in the calculating the Ferranti effect. Resistance is negligible, calculation of Ferranti effect. Let us consider a pi model. I'm not taking T model. This is a pi model. I'm considering pi model, pi network, medium transmission line, pi network, right? What is the sending end voltage? We know the directly equation for pi network. Vs is equal to 1 plus yz by 2 Vr plus zir. A is equal to 1 plus yz by 2. B is equal to z kada. So that's why Vs is equal to 1 plus yz by 2 Vr plus zir. That is the sending end voltage for pi network. Now Ferranti effect is occurring at what load? It is a light load or no load or a full load? It is a light load or no load. At no load condition, what is the current? No load is nothing but open circuited. If it is a load is open circuited, what is the current? Receiving end current, IR, 0. Current open అయితే current లేకపోతే current I mean open circuit అంటే current flow కాదు, IR is 0. So substitute IR is equal to 0. For open circuit, IR is equal to 0. Now that equation must be Vs is equal to 1 plus yz by 2 into Vr, right? Now I am just, so this is the equation, Vs is equal to 1 plus yz by 2 Vr. Now subtracting the Vr from Vs, subtracting the Vr from Vs from the above equation. Just ఈ equation లో మనం Vr ని subtract చేస్తున్నాం on both sides. Vs minus Vr, that is equal to 1 plus yz by 2 Vs Vr minus Vr, right? Now here first term Vr is there, second term also Vr is there. That's why taking Vr as common point. Vr into 1 plus yz by 2 minus 1. 1 cancel, that is yz by 2. Vs minus Vr is equal to yz by 2 into Vr, right? What is the y? Y is nothing but shunt admittance across the capacitor, right? So omega CL, and so it is by 2. And what is Z? R plus J omega L. So then Vr. Neglecting the resistance here for reactance is more than the resistance. That's why resistance is neglected. So R is neglected. What is the remaining equation? Vs minus Vr is equal to minus Vr. Why? Because J square minus 1 omega square L square capital L C. L is nothing but parameter length, right? Now substituting the values in the above equation, so In place of LC, substitute the 3 into 10 power 8 square. Why? Because omega is equal to 1 by root LC. The omega velocity of wave is 3 into 10 power 8, right? Meter per second. Substituting the values, Vs minus Vr is equal to, so from that above expression, so 1 minus omega square L square in 10 power minus 8 by 18. This value is always less than. Why? Because 1 minus anything less than 1, right? So 1 minus anything less than 1. Less than 1 is nothing but, so like this. Vs is less than Vr or Vr is greater than Vs. So this is the proof for Ferranti effect. For 2 marks, just define. For 5 marks, prove the Vs is greater than Vr also. Important, Ferranti effect. So therefore, the receiving end voltage is greater than the sending end voltage, and this effect is called as Ferranti effect, and it is valid for only long transmission line, medium transmission line, and also it is a open circuit condition also, right? So how to reduce the Ferranti effect, right? So electrical devices are designed to work some particular voltage. That means all the auxiliary equipments may work just some standard voltages, plus or minus 6 volts of rated voltage. Above that one, below that one, the devices, electrical auxiliary equipments may be damaged, and their winding may be burned if high voltages. Now Ferranti effect on long transmission line at low load or no load increases the receiving end voltage. This voltage can be controlled by placing the shunt reactor at the receiving end. So ఎప్పుడైతే రిసీవింగ్ ఎండ్ వోల్టేజ్ ఎక్కువైందో కన్జ్యూమర్ దగ్గర వోల్టేజ్ ఎక్కువైతే ఏమవుతుంది, హై వోల్టేజ్ కన్జ్యూమర్ దగ్గర వస్తే ఏమవుతుంది, ఎక్విప్మెంట్స్ మే బర్న్. టు రెడ్యూస్ దట్ వన్, ఏ షంట్ రియాక్టర్ is connected to the at the end of the transmission lines, right? Because of by using shunt reactor we can reduce the Ferranti effect. What is the shunt reactor? Shunt reactor is a inductive element. Just shunt reactor is nothing but inductive coil that may be connected between the line and neutral point. Phase ki neutral madhyalo connect చేస్తారు, such that they will compensate the capacitive current. Capacitive current తగ్గిస్తుంది. ఎప్పుడైతే కెపాసిటివ్ కరెంట్ తగ్గించిందో ఏమవుతుంది, కెపాసిటివ్ కరెంట్ వల్లే కదా విఆర్ అనేది ఎక్కువ వచ్చింది. బికాస్ ఆఫ్ ఛార్జింగ్ కరెంట్ ఆర్ కెపాసిటివ్ కరెంట్, రిసీవింగ్ ఎండ్ వోల్టేజ్ ఈస్ గ్రేటర్ దెన్ ది సెండింగ్ ఎండ్ వోల్టేజ్. రిసీవింగ్ ఎండ్ వోల్టేజ్ ఎక్కువ అవ్వడం వల్ల ఆక్సిలరీ ఎక్విప్మెంట్స్ డ్యామేజ్ అవుతాయి. సో టు రెడ్యూస్ దట్ రిసీవింగ్ ఎండ్ వోల్టేజ్ we may connect a reactor, shunt reactor in between the phase and neutral, that may reduce the charging current or capacitive current, such that VR is reduced, right? So this is the problem. This problem is already discussed, right? Now already discussed some problem. Go for the another problem. So a 220 kV 3-phase transmission line, right? A 220 kV 3-phase transmission line is 60 kilometers long. The resistance is 0.15 ohm per kilometer and the inductance is 1.4 millihenry per kilometer. Use the short transmission line model to find the voltage and power at the sending end. So this type of problem also we are doing in different values, but so we have to discuss it once again, and also calculate the voltage regulation efficiency in the line supplying a 3-phase load of A 300 MVA 0.8 power factor lagging at 220 kV, 300 MVA 0.8 power factor leading at 220 kV, right? This is the problem. Just they given R is equal to 0.15 into 60. So resistance is 0.15 ohm per kilometer. Ohm per kilo. Oka kilometer ki 0.15 per 60 kilometers ki anta 60 into 0.15. R is equal to 0.15 into 60, that is equal to 9 ohms, and frequency is 50 Hz. X, that is reactance 2 pi FL omega x is equal to omega L, right? 2 pi f and 1.4 in 10 power minus 3. So the L value 1.4 millihenry per kilometer. ఒక కిలోమీటర్కి 1.4 millihenry, 60 kilometers కి 60 into 1.4, that is x is equal to 2 pi L, 2 pi f, 2 pi f, 2 pi f L, 2 pi into 50 into L, 1.4 into 10 power minus 3 into 60, that value is given to 26.39 ohms. Now first receiving end voltage for phase, వాడు త్రీ ఫేజ్కి ఇచ్చాడు కాబట్టి మనం ఆల్రెడీ చెప్పాను, వాడు త్రీ ఫేజ్ ఇచ్చినప్పుడు కూడా ముందర మనం పర్ ఫేజ్ వాల్యూస్ కొనుక్కొని లాస్ట్లో దాన్ని అప్లికబుల్ చేస్తాం త్రీ ఫేజ్ కంటే. సో విఆర్ 220/√3 పర్ ఫేజ్ 127.0 kV. Now three phase apparent power is 300. They given 300 MVA, so 0.8 power factor lagging. Cos pi is equal to 0.8. What about pi? 36.87 degrees. Now apparent power is equal to 300 MVA at an angle 36.87. This polar form may be converted into rectangular form. We are getting 240 plus j 180 MVA, right? Now we have to find out, we know the apparent power, we know the voltage. Now find out the receiving end current. Power complex power P is equal to 3 VR IR cos pi, right? So but already the cos pi value, so this is the cos pi value. Apparent power is combination of total, that's why S by 3 VR. What is the S value? 300 into 36.87. 3 into VR is nothing but 127 at angle 0 into 10 kilo. Then we are getting 787.4 at an angle minus 36.87 amperes. So we determine the receiving end voltage, we determine the receiving end current. Now go for the sending end voltage and sending end current, right? So we know the formula. Vs is equal to Vr plus IR cos pi r plus IXL sin pi r, sin delta or sin order. Vr is 127 kV, I is equal to 787.4 amperes, and R is equal to 9 ohm, X is equal to 26.39. Lagging power factor, that is 0.8, cos pi 0.8, sin pi 0.6. Then calculate all these things. So Vs sending end voltage is equal to 145.13 kV. So this is the phase voltage. Now line to line voltage into √3. Vs line to line is equal to √3 into 145.13. We know the sending end voltage, we know the receiving end voltage. Now difference between these two, getting the regulation. Vs minus Vr by Vr into 100, then we are getting the percentage regulation. 251.37 minus 220/220 into 100, that is 14.26%. Now we know the regulation, then we are calculating the efficiency. What is the efficiency formula? Vr IR cos pi r by Vr IR cos pi r plus losses 3I square r. So first we have to calculate the I square. We know the Vr, we know the IR, we know the cos pi r. Remaining term 3I square r. Calculating the real power loss in the transmission line is I square r per phase. Then we are getting the three phase also. So now receiving power is equal to, so 300/3 into 0.80 megawatt. Per phase sending end power 80 plus, so loss, power plus losses. Therefore efficiency is equal to receiving end power by sending end power. Receiving end power is nothing but 80, sending end power 80 plus 5.58, that is 85.58 megawatt, sorry 93.47%. So this is the second one. So for lagging power factor, now leading power factor, what is the change here? For lagging power factor here plus IR cos pi r plus IXL sin pi r for lagging power factor. For leading here minus, that is the only change. So for leading power factor, voltage regulation maybe goes to negative also. Negative also. And efficiency for leading power factor also. This is for another problem. So determine the nominal sending end voltage current or for short transmission and medium nominal-π method also. The given Z 33.J104, that is 109.11 angle 72.4 ohms. Y is equal to J 10 power minus 3 mho. Now receiving end voltage per phase is equal to VR by root 3, that is 120.08 at angle 0 degrees kV. Now getting IR is nothing but, so this is 3 phase, that's why P by root 3 VR cos pi R, we are getting this value. For short transmission line, Vs is equal to VR plus Iz. We know the values, and substituting we are getting sending end voltage is equal to 135.87 at an angle 4.62 degrees kV. For line to line into root 3, right? That is 235.33 at an angle 4.62 degrees kV. It is a short transmission line, right? For short transmission, there is no capacity effect, right? That's why sending end current is equal to receiving end current. So Is is equal to IR is equal to 0.17 at an angle minus 36.87 kVA. So sending end power factor is cos of 36.87 plus 4.62. Angle between the Vs and Is. For nominal-π method. For nominal-π method, we know the given ZY. We know the ABCD constant for nominal-π. So A equal to G equal to 1 plus YZ by 2. B is equal to Z. C is equal to Y into 1 plus YZ by 4. Now substituting the Y value, Z value, and we are getting A, B, C, D values separately. Then for the basic definition, Vs is equal to AVR plus BIR. Is is equal to CVR plus DIR. By that, we have to determine the sending end voltage and sending end current. Sending end power factor is nothing but, so 10.23 minus 5.72. And sending end power is equal to root 3 VL cos pi. We are getting 52.4 megawatt. Like that, we have to determine the problems. This is the another problem. A 132 kV 50 Hz 3-phase transmission line delivers a load of 50 megawatt at 0.8 power factor lagging at the receiving end. The generalized constants of transmission line are A equal to D equal to 0.95 at an angle 1.4 degrees, B is equal to 96 at an angle 78 degrees, C is equal to 0.0015 at an angle 90 degrees. Find the regulation, charging current, Nominal-T method by using Nominal-T. The given receiving end voltage 132 kV. That means per phase there is a 3-phase system. Per phase is nothing but 132 into 10 cube by root 3, that is 76210 volts. Receiving end current IR is equal to 50 P is equal to root 3 VR IR cos pi R. Therefore IR is equal to P by root 3 VR cos pi. Therefore IR is equal to P by root 3 into V into cos pi, that is 50 into 10 power 6 by root 3 into 132 into 10 cube into 0.8. We are getting IR is equal to 273 amperes. We know the cos pi R angle 0.8. Cos pi R is 0.8. What about sin pi R? 0.6. Now taking the receiving end voltage as a reference, that is VR is equal to VR plus J0, that is 76210 plus J at an angle 0 degrees. IR is nothing but IR at an minus pi R, so 273 at an angle minus 36.9 degrees. And we know the sending end voltage Vs is equal to AVR plus BIR, and substitute all the values. These are all, so here multiplication is there. We directly multiplied in polar form, plus this is also multiplication, directly multiply with the help of polar form. Now here plus is there, right? So that's why go for the rectangular form. Directly మీరు క్యాలిక్యులేట్ లో చేయొచ్చండి, ఈ కాస్లు గీస్లు ఏం లేకుండా డైరెక్ట్ గా So 7 to 400 at an angle 1.4 degrees plus 26208 at an angle 41.1 degrees ని డైరెక్ట్ గా మీరు రెక్టాంగులర్ మారిస్తే థర్డ్ రెండు లైన్ వదిలేయచ్చు. So this may be converted into rectangular and this may be converted into rectangular. Now adding both and we are getting the 92,128 plus j 18996 that is equal to 94,006 volts. That is the sending end voltage. Sending end current Is is equal to CVR plus DIR. Same. First multiplication is applicable for polar form. First we have to multiply these two and then these two also and convert this one into rectangular form, this one into rectangular form. We don't use all these things. With the help of calculator we have to convert and then adding. After then we have to convert polar form. So 128.2 sorry 211 minus j36 is the sending end current. What is the capacitive current? Capacitive current is the difference between the sending end current minus receiving end current. So we know the sending end current and we know the receiving end current. So difference between these two we are getting the charging current, that is equal to 128.2 at angle 93.1 ampere. Therefore regulation, what is the regulation for transmission line? Vs minus Vr by Vr. What is the Vs here? Short transmission for Vs by A. Vs by A minus Vr, right? We know the A value, the given. That's why Vs by A. Suppose it is short transmission line, A equal to 1. Vs minus Vr by Vr. It is a medium transmission line. So that's why regulation is equal to Vs by A minus Vr by Vr into 100. We know the Vs value, we know the A value, we know the Vr value. Then calculating the regulation is 30%. Another problem also, there same similar problem. They given ABCD constants, right? Determine the sending end voltage, sending end current, sending end power also and efficiency, right? As usual, first receiving end voltage, it is a 3-phase. First convert single phase 110 kV, so that is 110 by root 3, 63.5 kV. This then find out receiving end current P by root 3 VR IR, that is root 3 VR, getting 262.4 amperes. As usual, taking VR as the reference, 6350 plus 63500 plus J0 and IR is equal to, so 262.4 at minus cos inverse of 0.8 power factor they given. That is the IR value. As usual, from the phasor diagram, Vs is equal to AVR plus VIR from the nominal-T method or π method. Vs is equal to AVR plus VIR. Is equal to CVR plus DIR, right? Then we are calculating the sending end voltage first and then sending end current, then charging current IC is equal to IS minus IR. Sending end power is nothing but 3 Vs IS cos pi, right? So efficiency is equal to receiving end power is nothing but output power by input power. So getting 82.3%. Like that they are asking problems. So this problem already discussed in the first class itself. This problem is also. All the problems will be discussed in the last class itself. Once you have to go through all the problems once again, right? You have to first second unit is nothing but calculation of voltage regulation efficiency for short transmission line, for medium transmission line, for long transmission line problems. Then ABCD constants for short, medium, long. What are the problems? Then Ferranti effect, surge impedance loading, charging current. Small topics. So, like that we go for the problems also. Go through all the problems and theoretical concepts also, right? Is there any doubt? Please ask me. So tomorrow class we explain the I explain the surge impedance loading, and charging current. So at that class, so the EPTS second unit is completed. Next class, tomorrow class, the second unit is completed. So is there any doubt? Please ask me.